Now we will use the yellow. Yes, yes. So saw that thermochemistry earlier in the Sarapalli sir lecture, right? So for that thermochemistry, we use the frequency calculation, right? And it has to be done on the optimized structure, not the random structure. So we will use that benzene structure what we have optimized and do the its frequency calculation. So you open that optimized file. So you go to the file and open. Go to your desktop and you see the benzene of log. It should extension should have the log file, right? You select this log file. Everyone is able to open that optimized log file. Yeah, that is not it. Now you open that log file and for that benzene. And also make sure that we optimize the monomer, one benzene molecule. Next, we will do the dimer, the two benzene molecule in the same window we will optimize and see that what is the effect of dimerization, right? So first we will put that frequency calculation. It will take time to run, and in between we will do the dimer calculation for that benzene. So everyone open that log file, optimize benzene structure. You go to the Rosary sector. Yeah. Okay. Log file. Yeah. Everyone open that log file, Benji. Okay. So now do the same calculation, Control G shortcut, and go to the frequency calculation. Do the calculation setup. Do the frequency, I mean, select the frequency calculation. And you will see that since you taken the optimized structure, so that the DFT level of theory is same because you take the optimized structure. If you take the different structure, again you have to set that DFT and with element the basis set. So since and note down, if you optimize for the DFT with element 61G basis set, you have to do that on the same level of theory, the frequency calculation. Otherwise, it is a meaningless calculation because you cannot compare because you are optimized frequency calculation. We are doing only the optimized structure. If you change the basis set or the level of theory during the frequency calculation, so at that level, the initial molecule is not optimized, so it will not get the correct value. So make sure that this DFT B31161G is already there, and you change the title so that you don't get confused. Submit this job. No, job time you have to change the frequency. You just open that. So it will take the time. You can minimize that window. And now you draw the dimer of benzene molecules. Right? In the same window, you have to add 2 benzene molecules. And make sure it should have the optimized benzene molecule, not the initial that you take from the Gauss view. Use that log file benzene and make 2 benzene molecule in the same window. Okay. Yes, sir. No, carbon select ಎಲ್ಲ So you can see that you can check that your frequency calculation is completed or not. Hopefully it has to be completed. So just close this. We are not going to open this file. We will use this later. That frequency calculation. Everyone. Okay. Now again open that optimize benzene structure. Go to the file and open. Okay. Once you open that optimized structure, now you go to the new structure. Okay. Here you see if you left click on the blue window, definitely it will CH4 will come because in the gray window CH4 is there, right? So we have this optimized structure. You just click this one at the top level where the benzene of log is there and put Control C, right? Go to the top section of the optimized opened benzene structure. Click on the that log part means upper part and Control C. You will see that the in the gray window benzene is appeared, right? So now the active window has the benzene structure, right? Now if you click that in the blue window, it will add the benzene. You want dimer, you you can add two molecules, right? Yeah. So everyone, you have got two structure. You can centralize this structure by clicking this one, that center. You will see that will appear in the center so that you will not miss the any bond. By clicking left mouse click, you can see you can rotate that it is in the same plane, right? And it has some distance between the two benzene molecules. So it, but in case of dimer, it should not be like because everyone can make the two structures with different distance, right? So if you want to slide a specific molecule or rotate, first you press that alt keyboard in key, and you can rotate this molecule. Only single molecule it will rotate. Use the alt key and select any atom in the one benzene segment, and you can rotate it. Everyone is able to do like that. Okay, everyone made the demo. Using note down the keyboard shortcut key. Using Alt, you can rotate in all direction. So you can align the direction of that molecule. So it is not always planar molecule. When you are making the dimer, it can have orientation like T or some bend shape, right? And if your distance between two benzene is too much, you can slide this using Alt and Shift keyboard. Use the Alt and Shift simultaneously, and you can slide that one benzene mid ring close to the okay. So now you can also rotate this part by Alt plus Control. Since it is a symmetrical molecule, so it will not affect much. But suppose you have the functional group OH and you have to orient the OH to the specific direction, so that time it will be useful. Okay, everyone made that diagram. Now give the calculation on the same basis set. Always write the name of the whatever you are doing, because later you will get confused which log file is there. So you write complete name so that they will not.
Like we will be optimizing it or
No, we are optimizing because yeah. So we will optimize that part. You can put benzene dimer or the sort. You can put the same name here. Yeah. So you put the calculation for the dimer optimization. Frequency calculation. Open the log file for that frequency calculation. You can minimize this part. Thermochemistry, Musarabali said that for n number of atoms, how many frequencies should be there? Anyone? Three n minus six, right? Can you tell me the number of frequency for this benzene molecule? Calculate the simple method. Yeah. How many?
minus 36
Three n minus six. N is the number of atom. Here you can see 12 atom is there. Apart from electron we also mentioned, but we are interested in atom. So 12 atom is there. So 3n minus 6, how much? 30. So you in that blue section, make sure you have opened that frequency optimized calculation, right? Not that optimized structure. It should be the optimized frequency structure. So you go to the result section and summary. You go to the result section and see the summary. So here your calculation summary is there, like log file type is there. It is frequency calculation. B3 lip is there for the restricted calculation. That is the different part. Basis set is there. Charge we do not put any charge now because it is a neutral molecule, so it is showing zero charge. Singlet, it is coming due to the string means multiplicity. It is a it does not have any radical or extra charge. That is why it is singlet. So this is the summary, but and go to the last opt tab, you will see that it is a converge all the parameters. But we are interested in this thermochemistry part. So open the middle tab, this is the thermochemistry part. So it is showing imaginary frequency is 0. But how we can verify it? Anyone? Yeah. It's showing imaginary frequency is 0. You for a moment you just cross this one and select, go to the result section and go to the vibration. Click vibration and scroll down and see how many vibration is there frequency. So it is matching with the 3 and minus 6 mode, right? And you can see all frequency as positive, starting from 421 to the 3226.73. Right? So for this is the actually frequency calculation is also called the vibrational calculation, vibrational frequency calculation. You can select any frequency and start the animation. It will show that at which bond length or bond angle it is vibrated. You can see by rotating. At this frequency, it is vibrating like this. Select frequency. Yeah, select first one so that yeah, you can rotate. Sometimes it is symmetrical. I will not so you can rotate. So it is a global minima. That is why its all frequency are positive. Those who are interested in transition state calculation, you will find a one single negative frequency. That is also called the imaginary frequency. Those who are interested in the finding the transition state. So that also give the confirmation. This positive frequency also give the confirmation that we are having that its true minima. Otherwise, sometimes it has 3 to 4 negative frequency. That case, you have to repeat your optimization because if you are looking for the ground state minimum, or if you are getting exactly one negative frequency, then it is a transition state. That if time permits, you can.
So if even if you make something wrong and get one, but still it's a transition.
No, that time you can partially claim that it is a transition state. That time you have to again do the one IRC calculation that will connect the reactant and product. This will confirm that it is a true
Whether
transition.
this is right or wrong,
Yeah.
validate.
Okay, so this is only for the checking the positive frequency and the number of frequency. So it has 3 n minus 6, 12 atom. It is having 30 frequency. All are positive, so it is true minimum, right? Now close this frequency part and go to the result section again, summary, and go to the thermo. So basically, it has created a log file earlier during the calculation, but this cause view is summarizing that thermo part. That is why it is saying imaginary frequency is 0, because in case of transition state, it will show a imaginary frequency of 1, right? And temperature by default, it is calculating to 98.15 room temperature. Pressure, all these parameters there. Here interesting thing is the 0 point energy correction. That during lecture session, we will just about that your 0 point energy. So basically, it is showing to at 298 Kelvin, right? If you do the calculation at 0 Kelvin, that 0 correction will be coming to the 0. Here it is coming 0.10 RT. So it is due to the temperature correction, it is giving some additional correction values that has to be added, right? And this electronic energy is the energy of this benzene molecule of the specific basis set, what you have set in during the calculation, right? So here, due to thermal correction, you saw already saw in the lecture session that how the parameters is calculating thermodynamic parameter, like first they are calculating the electronic energy, then enthalpy, then temperature correction is there, then entropy is there. So all this summarized in that Gauss beautifully. So you can see that thermal correction to the energy part is this one, Hartree. For the enthalpy part, it is this one. For the free energy, this one. Again, they are summing with the 0 point energy and giving the energy. And lastly, it is also giving the entropy values. So once you have delta H values, so and temperature is 298 Kelvin. So delta S you can find from that. I will show one Excel sheet that how you will calculate. So for the thermochemistry analysis, we have to do the first, you do the optimized structure of the molecule, then do the frequency calculation of the same molecule at the same basis set level, right? So you have suppose you have reaction system like A plus B give to AB, right? So if you are calculating delta, we are seeing the delta value now. So you have to calculate separately for A molecule, separately for the B molecule, and for the complex AB molecule. Then take the individual's energy parameter, take the delta value from product minus reactant, right? Product minus reactant. Uh, for that chemistry part, I will show one Excel sheet so that you will have idea. Okay. So in this section, we have these two molecule of this chlorophenol. It is a different system. It is not related to you, but we are showing that these two molecule in the red, it is showing that two reactant molecule is there, this one and this one, right? And this is forming a transition state, but this will not, we will cover this time, and forming that pyridioxine and HCl as a product, right? So for the every time you have to optimize first this one, since both are same, so you have to keep it same as. So whatever you got, you have got energy here, electronic energy. So that should be at the E, electronic energy. And what should be the, you got the 0 point correction, you have to put the as a JP column for the specific individual molecule, right? You can summarize this. Those who are not interested in doing the thermochemistry part, they only report this E values, which is not a correct method, right? Because you miss the correction parameter. And suppose someone if interested in the 0 point energy correction, some people are using this part E naught as a energy difference delta E. From delta E, you can compare that it is a exothermic or endothermic reaction. So it is also not a fully correct, but it is better than E because you have included the 0 point energy correction. So now that correction part, what we have here mentioned. Yeah, this one. So it is also included E plus 0 point energy. So it is giving the corrected value with the inclusion of the 0 point energy. So this is the correction in the energy, internal energy. Basically, it is internal energy. This is correction in the enthalpy. You can see here in that thermal correction to enthalpy, energy, and free energy. So this column is representing this these three values. And by default, it is Gaussian is calculating at the 298 Kelvin. We are getting that E values at the 298 Kelvin. Any doubt? Everyone is only looking. Yes. So that E value is the electronic energy what you are getting from this after optimization, right? So it is not. It is the same energy. If you open that optimized benzene structure, its energy you are getting same. Frequency calculation we are only doing to get these all additional values. So it is the optimized electronic energy of the benzene. So this is reported in the this part. And here I am giving one example that for the A plus B giving C plus D, this type of system. So here A is like in the red one. So you have to arrange the all individuals values in the sheet, and you take collectively at the 298 Kelvin what is the effective energy, including the all correction, all three correction in energy, which is the internal energy basically, correction in enthalpy, correction in Gibbs free energy, and make a specific table for the energy corrected value, enthalpy, and the G value. And that entropy part you are already getting from the air, right? For this case, because it is a different example. So here you are getting entropy part. So for each species A plus B going to C plus D, you have to calculate all these parameters, right? Anyone? Any doubt? And one more thing that in Gaussian, generally the default unit is the Hertz unit. So it is the conversion factor. 1 Hertz is equal to 627.509 kilocalorie per mole. So after getting all energy values like E value, H value, and G value, and including entropy, now you have to introduce the delta E. Delta is the E is the difference between total product side means C plus D's contribution minus the A plus B contribution. So delta A you got in the HAT, you can convert the in the kilocalorie. Same for the delta H, and same for the delta S and delta G. But make sure that calculating the delta G, you are using the basic equation of the thermodynamics, that delta H is equal to and delta G equal to delta H minus T delta H. So temperature you are already knowing that it is calculating at a 298 Kelvin, and delta H you are calculating. So from this you are able to calculate the delta G value, right? Any confusions? Delta H value that most of us have put in the slide, they have set of equation. Delta U and some NRT part is there, delta NRT part will be there. So it's including all correction here. The correction is there that so I am repeating again. Okay. So for thermochemistry calculation, you have to first optimize the structure. Like we already did the optimization of the benzene, and on the same structure and the same level of theory, we are doing the frequency calculation, right? And in frequency calculation, you have thermochemistry. In log file is there, but we are showing only summary. This software is showing the summary. It is very good. It is saving our time. Otherwise, in log file, all the details, calculation steps, all is available. So in the thermo part, you can see that imaginary frequency is 0. So that you can also confirm from that what exactly frequency it has using the vibration, right? So since it has all positive frequency, that means you got the true minima. No, not a transition state, neither a second order saddle point. It is a true minima. Yeah, example. Yeah. So after making your atomic energy, now we are adding, we are saying that some people are doing that correct, recording the energy value in terms of EA, which is not a correct method. So if you include the JP correction, means the vibration at the 0 Kelvin, so that part is somehow better compared to the E. But still, for thermochemistry is not complete here because you have to complete the delta G value. For delta G value, you have to see the contribution of entropy. What is the contribution of entropy is there? So that you have to include the all correction parameters, including in the internal energy, enthalpy, and Gibbs energy, right? And apart from these are the correction. Now you are using the EE plus this correction. E is there correction part you have to add. You are getting that individual value E to 98. Same for the enthalpy. It is E plus enthalpy correction. You are getting H 298. E plus J correction in G. You are getting delta G. And S entropy you are already getting from that input output file. That part. Any confusion? Yeah. For the E298, H298, and G298, we are adding that to obtain E energy from the calculation and adding the correction values. Like for the E298, you are using the E value plus correction value. And this correction value, you see that it is already include the JP. So here you can see that E is the obtained energy from your optimized calculation, and JP you have to get from the frequency calculation. And this correction value in Gaussian, it is giving that JP plus correction. So definitely, if you want to see the pure correction in the energy, if you then you have to subtract this value to the JP value, then you will see that at 298 Kelvin, what are the exactly correction term is there in the energy part. It is in internal energy part.
We can raise it to like 300 Kelvin.
Yeah,
We can do that.
yeah, you can do that. I will come later. So that part. So this is the total correction, including JP and the thermal correction in energy. Similarly, this is the total correction in enthalpy, including JP. You can see this value is more than JP. So JP is already included. So basically, we are adding this value, this E298, including this value, JP value, and this pure correction. Here it is included. That is why this value is the summation of this and this, because we JP already included, right? I'm repeating again. This E298 include three parts. One is the pure energy you are getting from the optimized energy. One is the JP, and another is the thermal correction to the internal energy. So summation of this correction is mentioned in this column. For specifically, we are also mentioned this column, but it is already, this one is sufficient. So this energy is the summation of this one and this one, right? Similarly, for the enthalpy, it is the summation of enthalpy correction plus JP plus the energy of pure energy. Similarly, for the Gibbs energy, right? And entropy part, you are this formula. Yeah, but it is not correct. Actually, it is coming from back, so it is equally give the same result. But this value we have to take the from here. Yeah, it is in the calorie mole per Kelvin, and if you convert in the Hartree, you will get.
So we have to convert it into Hartree.
Any specific,
we have to do it either in Hartree or in kilocalorie.
Yeah, better to do in the Hartree in all these things. Later you stay, you just convert. This will be the same energy. Otherwise, each time you have to get convert the everything. So after getting this all values, E values, H values, now you take the delta value from product minus reactant. So in this case, an product part is this part highlighted in yellow, and reactant part is highlighted in red. So you take that this value minus this value. Forget about this CS value. That will be the different part. And same for you are getting the delta E value, and for the same delta S you can calculate delta S. You take the difference between the product and reactant. You get the delta S, and delta G. You can either calculate this way, or this three value is enough if you have the temperature, because if temperature is 298.15 Kelvin, right? So this way you see that Gibbs energy value is 0.88. Anyone, is it feasible or not? What this reaction says, delta G is coming 0.88 kilocalorie per mole. Feasible or not feasible? Why? Because it is not a spontaneous process. For that process, we have to put additional energy. Okay. So this is the thermochemistry at the 298 Kelvin. Those who are interested in the means for the higher temperature, you just mention the temperature parameter in the frequency calculation. I will show you how to do that. Now you again open the optimized frequency calculation file. go to the calculation part. Open the frequency optimize file, log file, and open the calculation part. In the additional keyword, you just write temperature equal to 360, 600. You can see that after writing, it is also mentioning in the keywords. Yeah. So this will give the electronic energy. It should have same JP energy. It will change or not? Definitely, it will change. Because at 0 Kelvin it is 0, but if 290 it is showing some positive value. At higher temperature it will be more value. So it will change the JP value and correction value is in all, either in the thermal correction, enthalpy correction, and delta G. You can also mention in the title so that since you already open the optimized file, so you don't need to change the type of calculation and basic set and theory level. So you just submit that part and rename at benzene frequency at the rate 600. So it will take time, just leave it on. So anyone got the optimized structure of the benzene dimer? Still running? It will run. We will continue tomorrow. No. So now we will set another calculation for that optimized benzene structure.
I have a question.
Yeah.
When you are calculating the product minus the reactant, you are adding the products together minus the spin. Like period of thin and exhale, you add the value.
Yeah, it is. It has to be for the thermochemistry calculation. You have to do the separate calculation. During calculation, when we are getting the transition state and all value and interaction value, that time collective values should be there. But during the thermochemistry calculation, you have to separately calculate A plus B giving C plus D. You have to collect like individual C, individual D, individual A, and individual B, and take the difference. That's okay. So right now, two run is going on. Just open one more time the optimized benzene structure, and we will do the NBO calculation because it will take the time. We will do that, put the calculation. By tomorrow, definitely it will be come over. So tomorrow we will discuss the NBO part. You have to open the benzene op log. And one more thing, if you are doing the frequency calculation either at the 600 or 300 the room temperature, the structure will not get changed, means coordinates. It will be remain same. So for the further calculation, you can use that coordinate also because the coordinate is not going to change. Because frequency calculation, we are only seeing the thermochemistry and the temperatures effect. So optimize this part and go to the calculation panel and at the open that pop analysis, population analysis there. We just open that same optimized structure. Go to the job type because we already optimized this structure. This time we have to do the energy calculation. That optimized benzene structure, we need to do the energy calculation, and in addition to this, we are doing the population analysis calculation. Keep method and all this same. Go to the title section. You better change its name. And go to the pop section. Here you can do the population analysis two whether either you put the keyword for that population analysis. So in the additional keywords you write pop equal to NBO. Pop equal to NBO. Population analysis for the NBO. NBO part. Job like LPG होता है और by default it is if you are not using any by default it is so but it is becomes very but if you are not sure about the keyword, you can select here also no NBO to select the full NBO. You see that also in the keywords it is highlighted pop equal to NBO in the keywords, and also save NBOs. Two changes there in the NBO section. One is perform NBO calculation, give it the full NBO, and save the NBOs. So in between, I will give about the energy for the dimerization that you already put the dimer benzene calculation. It is still running. So once it get optimized, you can get the difference between the combined energy and minus the single energy. But two times because it will we will see the effect of the dimerization. It is additional interaction is there between the benzene molecule. So that we will cover tomorrow. But I'm just giving the basic idea why we are doing the dimerization. Because benzene is a polar or non-polar. Non-polar. And water polar. So water has the H bond interaction between when you form the dimer of the water. So it has the H bond interaction between the two water molecules, but not in the case of the benzene molecule. So you will see the effect of dimerization in the polar as well as in the non-polar. That we are trying to do that. So just put this NBA calculation. Minimize this. And last molecule you should make also the dimer for the water. So again, I am repeating this part how you are making two structure in the same window. Open the optimized water molecule. All have put that NBO calculation. The same level you are optimizing. Whatever the level of the optimizer, you can repeat them again. Means optimize that value, then you do the only entry part. Yes. Yeah. Maybe we have different because you can make it get take time.
So I have to do dimer and water optimize water dimer, then frequency.
Order. Okay, diver part is for saving time and giving
So I have done that. Like
water diver.
water dimer I have like done it. So now frequency and yeah, now.
So that how the you can see how
And one more thing, this this frequency calculation, that's, yeah, it has also been completed. No?
So I think NBO part is done, but we will see its analysis part tomorrow. And 600 Kelvin also it is done. That is
I'm just where do I get the 600?
keywords. Temperature equal to 600. So I'm also putting the timer calculation for the water. make sure for the dimer same basis set should be there, like DFT, B3 leaf and 631G. Optimize single water molecule. Since putting on the same two molecules, then optimize again. It will be so the infection. Okay, one last analysis is there that I think your frequency at 600 Kelvin is also over, right? Frequency at 600 Kelvin. So we will just compare that what are the changes in the frequency at the 298 Kelvin compared to the 600 Kelvin. So all calculation you just keep it as running. Open separately both file benzene frequency normal and benzene frequency at 600. Of course, you should open the log file. That I think both are same. Yeah. So left one is the benzene frequency calculation at normal room temperature 298.15 Kelvin, and second one is the benzene at 600 Kelvin. So first we will check the vibration of both. So this one is the for first case. So you can see at different temperature frequency is not a function of its temperature. That is why the vibration is coming the identical in both cases. Everyone able to open that frequency. Again, I am giving you the how to set the temperature, different temperature. So for new calculation, you just write here in the additional keyword temperature equal to 600. If you want to at the 900 Kelvin, the temperature equal to 900, right? So it will not change any geometry. It will not change frequency rotational value, but it will change the JP value and the thermal correction in energy, enthalpy, and the Gibbs free energy. So I hope you already observe that there is a no change in the frequency values. So you just cross the both value. Now we'll see the thermochemistry values. Go to the result and summary for both cases and highlight the thermo part. Thermochemistry here is mentioned. Here you can see the difference. No imaginary frequency because it is a true minima. temperature is different, 298.15 and 600 Kelvin is there. Electronic energy you will get the same because it is the optimized energy. We are giving the frequency calculation and the temperature variation only to see the JP and the thermal correction. You can observe that in the JP correction it is not much improved. Why JP is not improved? Anyone? In both cases. Why? Because 0 point is the bottom at 0 Kelvin. Depend on the temperature. So that is why it is taking at the 0.0 Kelvin values. But you will see in the correction values there is a deviation. So it is somehow improved because the temperature increase. In some cases, delta NRT is temperature correction is there more at higher temperature. Correction will be more. You have only correction values. That is why at in this example, I can demonstrate what is the effect of temperature. This is the delta G value at the 298 Kelvin for the specific reaction, right? So delta G positive value shows it is a it's not a spontaneous process. You are increasing the temperature in the same case. The delta G value is become more positive value. This shows from this analysis you can figure out that whatever their reaction is there, is it feasible or at low temperature or high temperature. So you can tune using that different temperature analysis that it is at higher temperature it is feasible or at the lower temperature it is feasible. Okay. So up to this, any question, any doubt? Please feel free to ask. And apart from this, some additional files are there. Like this one, I will share it to you. Here basically include that which type of calculation is there, like electronic structure determination, geometry optimization, frequency calculation, transition states, reaction pathways. For those who is asking for the protein part, talking to you. So that part can be also basically it is the interaction for the protein and ligand type of you just introduce it is the binding of ligands and the protein. So it is the same. For the binding calculation, we will do the tomorrow part, but not on the protein for the dimer case. And you can also calculate the potential energy surface that you are also aware that Musarraf sir mentioned that part. Rate constant using this, you can also calculate the rate constant, reaction energy, activation energy. So these are the all possible calculation you can do in the Gaussian calculation. And Gauss view is the graphical user interface. You can easily make the molecules and do the calculation and set the different keywords and do the different calculation for NBO temperature calculation, means temperature at high temperature. So I will share this few materials is there with you. So for today's session, we are concluding at that time. If you have any queries, or you can not in the WhatsApp group. You can you write your queries. You can ask tomorrow. tomorrow we'll cover the MBO analysis that we have done. Calculation is already done. We do the MBO analysis part, and
Link type.
in time permit we will start the transition state calculation also. Okay.
So that concludes day one. So tomorrow we start at what, 10 o'clock? We start at 10 o'clock. In this periodic DFT. So this all resources will be actually shared to you, including the recording, everything.